Oh, God, there we go.
Thanks, Rich, for getting us started today. I will be presenting on geospatial reprojection in Python. This is very much a work in progress. It aims to become a guidebook and profiling results. And this was done with the help of several people. I want to acknowledge my team members at Development Seed, especially Amy, as well as the Pangeo community, especially Eustace and Michael for helping out as I was developing the content. Just a bit of background for why I'm giving this talk right now. I care about resampling from a few of my different hats. So I'm a cloud engineer at Development Seed, and I regularly need to resample data to do my job. I also care deeply about Pangeo because I think it can provide an awesome open source meeting ground for different software developers, scientists, and can help in general move the ecosystem forward. And I think Tom Nicholas's his led discussion last December kicked off some really excellent conversations. One of those was around resampling. So I'd like to revamp that conversation and have a nice discussion after this talk about how we can move that part of the ecosystem forward. Lastly, I really love mapping. I worked in the past on the generic mapping tool, which is a processing and visualization libraries. And resampling and in general projection is essential for any 2D representation of three-dimensional data. So I really appreciate all the libraries we have because it enables us to make great earth science visualizations. Putting on my Pangeo hat for a second before I get started, I want to give a plug for this fall semester's showcase series. Please attend the future showcase series, regardless of how well or poorly my talk goes today. I promise they'll be fantastic. We have one starting next week on the Project Pythia cookbooks updates. So they'll be every Wednesday, alternating between 12 and 4 Eastern time. So all the talks are on the Pangeo.io website, and we'll post announcements on the discourse a week in advance. Before I get started, some caveats. This is very much a work in progress. As I mentioned, I just want to prompt a discussion more than anything. Because it's a work in progress, the recording itself will very quickly become out of date. Please look at the repository that I'm building for updated information, and also verify and fix any code before you use it. And I would love it if you contribute fixes back into the code base itself. To ground this discussion and make sure we're all having a shared understanding, I wanted to start with some definitions. These definitions are used, I think, in different ways by different people. So this is the definition that I will be using today. Reprojection is the changing of the projection of a data set from one coordinate reference system to another. So on this side, I have iframe showing the geocomputation with Python cookbook, and one of their figures showing the reprojection of a point from a projected coordinate reference system to a geographic coordinate reference system. You can see how the buffer around the point is distorted when you go in with that inverse projection. So in this example, because it's a point, there's no grid, you're just reprojecting, you're not resampling. Alternatively, you can have resampling or regridding, which is to change the grid structure. When people talk about this, they often talk about changing the resolution, but this doesn't have to be the case. You can have the same resolution, but different cell geometries. So for example, and also how the bounds of the cell reflect the data. So whether it's, for example, pixel or grid line registered data. So an example of this regridding without reprojection is commonly COG overviews, which are lower resolution versions of the same data set that can simplify visualization and analysis. So this is an example from the Cloud Optimized Geospatial Data Formats Guide, where they're showing different overviews of COGs. So as you go to the higher levels, you get lower resolution versions. And then lastly, what I'll call warp resampling is changing the resolution and the projection of a data set. XKCD has some really fun projection or warp resampling related comics. And I think warp resampling and reprojection are commonly used interchangeably. I find it difficult to stick with warp resampling, but I think if we all use that language when we mean changing both the resolution and projection, it would make some things more clear. I'll go over a couple factors that matter a lot when considering warp resampling. One is the grid structure, so how your data relates to the coordinates reflected in the data set. Three common options are rectilinear, which can be described by one-dimensional latitude and longitude coordinates, curvilinear, which requires two-dimensional lat and long coordinates, and then lastly, unstructured, where you need a list of nodes to describe the grid coordinates. And NCAR's climate data guide, which is linked at the bottom, provides some really good information to understand these concepts. The last, not the last, but one other important component of warp resampling algorithm, or really any resampling algorithm, is the specific aggregation method used. This is a long list of many of the options. Again, NCAR's Climate Data Guide provides more information. Most software libraries also include information about what given algorithms they have implemented. That's the background, and now we'll get into the real content, which is what geospatial warp resampling looks like in Python in 2024. Actually, one more background slide. There's a lot of reasons why you might want to do this. And two common ones are because you need to co-register data sets. So your data sets, when you do analysis, machine learning, or create a mosaic, need to be on the same grid structure, or you want to visualize your data. So render it on a two-dimensional screen or piece of paper. Now we're going to get into the crux of the talk, which is resampling methods in Python. So this, I'm going to tab over to here, which is an easier way to navigate, is a diagram showing what resampling in Python looks like today. So at the top, we have the category, resampling methods, and then Eustace had a really great post on the Pangeo discourse a few weeks ago explaining the different components that are included in a resampling method. So we have that you have to find the indices of the pixels to aggregate. This can be either cells that are contained within the target cell or nearby, depending on which specific algorithm you're using. Separately, calculate the weights associated with those, and then finally perform the aggregation. And there's a set, like many libraries that actually do all or different components of this. So just to walk you through this kind of box here, can someone share if they can see my cursor or not? That would be helpful for, yeah, you can. Okay, so on the left column is the libraries that actually implement these nitty-gritty components of a resampling method. So that includes GDAL warp, which is a C library, ESMF, which I think is C and Fortran, GMT, which is C, and then there's a couple that are more pure Python from my understanding. Xarray regrid, which is built on Flocks, PyResample, which is built on PyKDTree, and Xcube, which is built on PyProj. Moving to the right, you have wrappers around these core libraries. So for example, since in order to use GDAL in Python, you have to use a wrapper or a Python API. GDAL warp is the Python API that's distributed with GDAL, or at least it's the specific component that does the warp resampling. Similarly, ESMF comes with ESMPy, and GMT has the PyGMT wrapper. We also have a lot of APIs that build on even these core Python APIs. So especially in the GDAL ecosystem of tools, Raster.io provides a higher level API that simplifies the GDAL Python API. And then there's a lot of tools that wrap that and extend it to make it more user-friendly. So that can include Rio Xarray, which is designed to support Xarray data objects when using Raster.io operations. You have GeoWombat, which is intended to simplify user code. ODC Geo, which defines, one of the things it does is define a geobox for storing information about the coordinate reference system. And I think GeoUtils has a similar goal. And then on top of ESMPy, we similarly have XESMF to work with ESM or ESMF regridding in X-ray. So this is like a lot of tools, and it's really hard to understand which one to use and when. So to address that, I'm doing a couple things. One is building a guide that is going to include code examples of each of these different methods, as well as profiling results. What doesn't exist in here right now is a mapping between these different libraries and the grid structures they support and the resampling methods that they implement, which is what will like most often guide what you need to do. But it's a work in progress. I wanted to kick off the showcase series on September 25th. So moving past into the actual content, what we've done here so far is some memory and time profiling for a few of these many different methods. And I have done this on the Mir SST data set, which is this experiment is designed to be like one of the more challenging ones you could get when using a rectilinear data set. So Mir SST is 0.01 degrees resolution for the globe, which comes out to, I think, like 36,000 by 17,999 coordinates. So it's quite big. It's stored in netcdf files on S3, and Earth Access provides a really awesome library for authenticating and downloading data from NASA's repositories. So this data set, this notebook just downloads it so you can use it locally, also virtualizes it for an extension of these examples. And then also you could use Earth Access's login method to actually just stream it from S3. Secondly, these notebooks for each of these different resampling libraries, it's designed to have a different combination of drivers and access methods. So this is an example of a notebook that creates zoom level 0, so 256 by 256 global raster data set using GDAL's like built-in Python API. And so we do this for different drivers like netcdf versus one of these has HDF netcdf, and then using VSIS3 or like, for example, doing it locally. And this is similarly for different libraries like Open Data Cube, XESMF. Unfortunately, although XESMF is in like probably the most commonly used one, it's in the work in progress section because I discovered that we need to wait for the next release of ESMF for XESMF to work with a data set of this high resolution. But if you use this code with a lower resolution data set, it should work. And then I ran PyInstrument to get the amount of time it takes to generate that zoom level 0 tile for each of these different methods and drivers, and also used memory to measure the peak memory usage for the tiling operation. So this is like, and the goal here is to eventually extend this out so you have a full kind of parameter space of combinations of methods, the drivers they support, virtualization methods, which would include like Kerchunk reference files or GDAL's tile raster virtualization method. But already we can see some kind of interesting components. The like biggest takeaway is that if you want to do this with a remote file, which is line 3 and below, it either takes a lot of memory or a lot of time or both. And I think it would be, and like our goal here is to use the more in-depth profiling results to maybe motivate development into these different libraries. But we can see for the local example, for example, GDAL itself doesn't take much more peak memory than the data set itself. And it's, for this size of resolution, not that bad, 10 seconds to regrid it down to 256 by 256. We saw that there's the biggest difference is actually where the data set's located. So that brings us back to this diagram. I focused earlier on the resampling method, but really when you're considering this type of workflow, you have to consider all the pieces of resampling. So that includes not only resampling method, but also how you're representing the data in memory. So that is comprised of, let's see, how you're representing the arrays, like if you're using a NumPy array, a Dask array, or a cubed array, how you're representing the metadata using OGC versus accessors or libraries that more provide a cataloging plus metadata service like intake or stack. And then whether you're using higher level tools that maybe even inherit from the X-array, data array, or dataset classes and build a new data object. And even more importantly, we have to consider how the data is stored and how we're approaching I/O. So this goes over like the many components elsewhere in the workflow that can influence these results. For example, is it NetCDF or is it ZAR, where it's more cloud optimized and easier to use in this type of cloud-based workflow? Similarly, do you have a virtualization mechanism on it? And how many layers in the access pattern workflow are you using, where you can build on these core C libraries with both Python wrappers as well as virtual file systems, and then also the back ends that connect with your different array libraries. So I think a key point here is that expanding this parameter space to include, or the parameter space of the measurements to include more I/O options is really key for understanding this. So from this, I wanted to start off our discussion point with just some observations I've made. In the making of this guidebook, a lot of kernels were killed. And I think we need a demo using a bounded memory approach like cubed. And it would be awesome if some of the libraries made that really simple for us. But I would be happy to chat with those people who can actually do that work and enable that as much as I can. I found that there are some awesome data cube libraries in Python, and I encourage people to work with the developers to make them even better. And please don't build another one because that diagram is already really big. I've been using X-Array for a while, and I find it really intuitive. I think this is similar for a lot of people. The most difficult libraries to learn were the libraries that used a different data model. So I'd encourage developers to use X-ray accessors rather than using a new raster data class, because it'll make it a lot simpler for people to adopt your approach. There's a lot to do here. This was really a last minute talk. So what's next for this guide? It'd be really interesting to generate a small tile from a large data set. This was an intentionally challenging problem of generating the coarsest resolution tile from a really high resolution data set, but it's and it's testing the bounds of what we can do with that type of approach, but probably we should just create overviews when we're doing that rather than creating a new tile each time. We also, I would like to add information about what grid structures and what resampling methods are included in different libraries in this guidebook, and then test with virtualized data, test with cloud optimized data, and test with other resampling algorithms. And I would like someone to help me test with Qt. So thanks. I think it's really cool that development team let me go down this rabbit hole. So thanks to them. Thanks to the Pangeo community. The few resampling posts that are on the discourse have been so fun to partake in, and in particular, Eustace and Michael, Eustace Megan. I'm sorry if I'm going to mispronounce your last name, and Michael Sumner really helped as I was scrambling to put this together. And then my work is currently funded by NASA Impact, so I really appreciate their support. So what's next for resampling in Python? Now we have a little bit of overview, and let's talk about it.
Thanks, Max. That's awesome.